Greetings, I am by name Olaiton Oluwaseun, and today I'll present an appraisal of riser concept for FPSO in Deepwater. This work is for our unit SSCH04 subsea riser design. For my objectives and content, here is what I'll cover: background on deepwater risers and FPSOs, main components of a floating production system, riser types already installed worldwide, assessment of flexible risers, the catenary risers and hybrid risers, current trends, future improvements and technology gaps, my recommendation for FPSOs in deep water, and finally lesson learned on how they relate to industry roles. For my background and state of the art, oil and gas exploration has moved beyond the continental shelf into ultra deep waters. FPSOs dominate remote or marginal fields because they combine production, storage, and offloading. But riser design becomes challenging. High hydrostatic pressure and payload and FPSO motions can create fatigue and buckling. Riser technology has evolved. Helitop tension riser gave way to flexible pipes, then steel catenary riser, and finally hybrid riser towers. For my component and floater unit, a floating production system includes the hull, topside processing modules, storage tanks, turret or mooring systems, riser and subsea wells. We have several floater types. We have the FPSOs, we have the semi-submersibles, we have the TLPs and SPAs. TLPs and SPAs have small vertical motion, so they can use top tension risers. But the FPSOs, on the other hand, move more, so we need riser systems that either tolerate motion or decouple it. For installed riser concepts, worldwide three main solutions have been used with FPSOs. We have the flexible risers and jumpers, which are common in Brazil and West Africa. They are easy to install. We have the steel catenary risers, which is supplied in Bonga, also Gulf of Mexico and elsewhere. The laser wave configuration add buoyancy to reduce fatigue here. We have the hybrid risers, like the Girasol hybrid riser tower or freestanding hybrid risers, which separate vessel motion from the main pipe. So for flexible risers are unbonded pipe made of several layers, like the carcass, the pressure sheet, tensile wires, and outer cover. They are highly compliant, so they handle FPSO motions well, especially with bend stiffness and buoyancy. However, they are limited by water depth, sour service, and fatigue in harsh seas. So today they are mainly used as jumpers or dynamic tiebacks. For steel catenary riser, these are welded steel pipes hung in a catenary shape between the seabed and FPSO. They are simple and cost-effective, but sensitive to FPSO surge and heave. Fatigue at the touchdown zone is a big issue. A laser wave configuration where buoyancy modules creates a wave shape reduces top tension and seabed fatigue. For hybrid risers stand vertically from the seabed, held by buoyancy cams, and connect to the FPSO with short flexible jumpers. This design decouples FPSO motions, keeps fatigue low, and allows quick disconnection in an emergency. They suit ash seas, like the ash areas, like the North Sea or Gulf of Guinea, where FPSO motions and storms are severe. Now, for the lessons and recommendations, from all concepts, hybrid risers give the best balance of strength, fatigue resistance, and operational flexibility for harsh deep water FPSOs. Steel catenary risers can work where vessel motions are moderate, and flexible risers remain vital for jumper sections. For the lessons also show how different roles contribute, like the design engineers select and analyze concepts, installation contractors manage tower tow outs and hookup, operators handle inspection and integrity management. So my recommendation is a group of SLOR or bundled hybrid riser tower for disconnectable torrent FPSO in harsh deep water. These are the main sources I used, cited in APS style. They include conference papers, journal articles, and offshore engineering reports. Thank you for your time.